Alrighty. We should be recording now. So welcome everyone to the MATLS 3E04 review session. For folks who don't know me, my name is Sarah. I use she, her pronouns, and I'll be taking you through the session. So I'm in my 5th year of materials I bio, but I took this course last year, so it's still pretty fresh. I'll be going through the 2023 midterm. So this is the one that I wrote last year. It is up on our course resource folder, which can be viewed. I'll write it right here at bit.ly/msc-course. You can find this as well as a couple other resources there. Some other disclaimers before I get started. So first of all, I wrote this course with a different prof than you currently have. So I had Dr. Zurab, who's a different prof than you're teaching. So I can't guarantee that the content is the exact same or that the test questions are going to be the exact same. I can only comment on my personal experiences. The other disclaimer is that, of course, I am a student myself, so I cannot be perfect, but I will try my best to kind of walk through these concepts. If at any point you have questions in the room, feel free to raise your hand or just say whatever. If you're online, I can't really see the screen, so I'm going to minimize y'all right now. So you're going to have to unmute yourself and start speaking, and I'd be happy to answer the questions. I will be posting these notes on the MS Teams, which if you're watching, you're currently looking at. But I'll be posting the notes right after the session. You're also welcome to message me on Teams or shoot me an email at any point with any questions, whether about this course, about the midterm, or honestly anything related to materials or life. Like, I'm happy to chat. Just no guarantee on the fast reply time because I also have midterms to study for. Okie dokie, that was a lot of words, but I think from then we're going to get started. My other disclaimer is that I do have somewhere to be tonight, so I cannot go late. Oh my god, hey, friends just walked in. Yeah, we're gonna plow on ahead. You guys can all look at my nose while you're online. It'll be really attractive, I'm sure. The other thing I wanted to mention is that if you have done this and you look at the solutions that are posted on course resources, I'm not going to be looking at those. I'm going through my own test actually. So I might approach it slightly differently than they do on the solutions there. They're just different ways of thinking about things. Alrighty, so for folks who just walked in, first of all, hi, welcome. It's nice to see you. We're just going to be going through the 2023 test. And I'm going to be talking half to you guys, half to my computer because there's people online as well. Alrighty, so with Dr. Zura, you can almost guarantee that one of your questions on the midterm and the exam is going to be drawing. Do you guys do a lot of that with Dr. Nana? Yeah, okay, beautiful. I would say the same thing then, because these drawings are a really great way to test your understanding of the situations without making it too difficult in terms of math or too tedious. So I would make sure that you're really comfortable. Do you guys get a cheat sheet? Yeah, I'm seeing nods. Okay, so for folks in person, I actually, on the back of my cheat sheet, this is my cheat sheet from the midterm, I put all the different situations as the drawings. I understood it all, but I was like, just in case I actually forget how to do anything in this course, then I put it there, and it was actually really handy because I did have a minor freak out in midterm, and I didn't have to worry about it too much. So use your resources. That being said, we'll try and understand it here. So it's basically just asking us to sketch the concentration profile at different times for different situations. So we start. We have a sheet of copper between 2 sheets of nickel with some varying thicknesses, and we want to know what happens. So I'm going to start by just drawing the whole sheet. Ciao. So the first thing I like to do is just write out what I have. So I know that this is nickel, copper, nickel, and we have distances of 450 microns. This is 100 microns. This is 450 microns. Next, so we know that we have, what we're going to understand here is that the first thing, we just need to look at the situation. Because we're given these distinct lengths, what we know is that the size of the 2 different sheets is not, like, the difference between them isn't too big. So what's going to happen is that this isn't considered an infinite or semi-infinite surface. We're actually going to diffuse into each other and create some sort of uniform final answer. So we start, I'm going to color coordinate this, and I'm actually going to match it up to what I did on my test last year. So I'm going to put, I will do green for initial. I will do blue for short. I will do purple for long time. And I will do orange for equilibrium or steady state. So if you are colorblind, I recognize that some of these might be difficult to tell apart, but I think because there's so many colors, I don't know a better way to do it. So feel free to message me if you do have trouble differentiating between the different drawings that I'm going to be doing. So talking about initial, we know that we have pure copper and pure nickel. So if we're talking about the weight percent of copper, this is pretty simple. If we have pure nickel, we're going to be smack down at 0. We have no copper there, so this is going to be 0. And if we have pure copper, we're going to be all the way up. Oh no, I don't want an arrow. We're going to be all the way up at 100. So it's really just following those lines. And now when we start to think about short term, what's going to happen? We have less copper than we have nickel. So what's going to happen, what we can think about is the copper starting to diffuse into the nickel, right? So we have a little bit of this copper, and it's going to start moving in either direction, diffusing into the nickel. So instead of having this high concentration in the middle, I'm going to zoom in a little bit. Instead of having this high concentration in the middle, it's going to do a little whoop, whoop, and start to go down because we're losing copper, and we're kind of giving it to the nickel instead. Note that because we're at a short time, the big things to note is that we still have 100% Cu at the middle. And then we still reach 0% Cu, or 0% copper in the nickel region. So it hasn't fully diffused yet, it hasn't gotten all the way, but it's working there. When we're talking about the long time, essentially this process has just continued a bit more, but we no longer have these two standards. And that's the differentiator between long-term and short-term, is now we no longer have the initial conditions present. So it's going to look something like this. Now you may ask, why do we no longer have 0% copper at the edges? That's a really big factor that we've moved up. They were no longer at 0, and that's because the copper is now diffused throughout the entire block. It's reaching to the edges of the nickel. And then long term, what's going to happen is this is slowly going to homogenize as the copper diffuses more into the nickel, and we're going to end up with something that looks like this. This will be in equilibrium because it's all constant, it's all homogeneous. And this is all you have to do for the first question. So the keys here are really just to understand what is short term, what is long term, and that our concentration is not fixed at the edges. So that's going to change and homogenize over time. Are there any questions so far? Beautiful. Moving on, now we have a thin wafer of COO, cobalt oxide, I guess, in an atmosphere, and then we change the oxygen pressure. So I'm going to draw the wafer. Oh, before I go back, so all you have to do for this question is just draw. You don't need to label any concentrations. Theoretically, Dr. Zerup told us that literally nobody did this on the test, but if you wanted to be extra, because we knew these distances, you could have actually calculated what the final concentration would have been. Because it'd just be a ratio between them, right? Because we know that we have 900, microns nickel versus 100 microns copper, so it would end up being 10% copper, give or take, right? So you could have written that and you would have gotten a bonus mark, but literally nobody in my class got that. But in case Dr. Nanda does the same thing, you can all get bonus marks. So yeah. Anyways, jumped around a little bit, but moving back, now we have a thin wafer in an atmosphere with 2 atmospheres oxygen, and then it's increased to 1 atmosphere. So personally, when I wrote this, then I put everything down in terms of our atmospheres, in terms of our pressure. So we know that we start at 0.2 atmospheres oxygen. So our entire wafer, because it's been sitting in that, stop being an arrow. I don't want an arrow. Because it's been in this atmosphere for a very long time, then it's homogenized, right? It's thin. We know that it's going to go all the way through. So it starts at 0.2 atmosphere. So I'm going to call this PO2 ATM. But then we increase the oxygen pressure to 1 atmosphere. So what that's going to do is that's going to fix it on the outside at 1 atmosphere, 1.0. Because it's thin, and we assume that we're in an open container, then this 1 atmosphere on the outside will not be changing. No matter how much diffuses in, then the oxygen in the air isn't going to change in terms of pressure or in terms of concentration. And like the cobalt from the semiconductor isn't going to be diffusing out into the air either, or not in any meaningful capacity. So we're going to fix this at 1 atmosphere, and what's going to happen is just slowly over time, this line is going to move up to meet that 1 atmosphere, because we're going to diffuse that oxygen in to be at the same relative concentration. So if this is our initial, at a short time, it's going to be very similar to what we saw before, is that in the middle, we're still going to have our initial situation, but now just at the edges, we start to have a little bit of that a little bit of that concentration gradient going on. Long time, it looks very similar, except now we no longer have that initial condition. And then at the end, again, this is going to be equilibrium. I think I spelled it right. Because again, we reach some sort of horizontal value. It's steady state, it's homogenized, it's not, there's no concentration gradient present anymore. What you should know here is that what did it technically ask us? It did technically ask us to do a concentration profile, and I did pressures to represent the atmosphere on the outside. Technically, what is correct is that we have the equation C is equal to K star times the root of pressure, whereas K star is whatever constant you can find. So technically, to write this would be K star root 0.2, and this would be K star root 1 atmosphere. So I did lose marks for that on my test. But Dr. Zorov said that's just because he was being picky, and that, technically incorrect, but that's something just to be note of, is that we're given this in pressures, but we are sketching a concentration gradient. Any questions about that? Delay. Moving on, now we have a piece of clay saturated with water, and then it is placed in a sealed jar of dried air. So this is different than the last situation because now we're in a sealed jar. And what that means is that the concentration of the air will be changing with time. It's no longer going to be like constant at 1 atmosphere oxygen, for example. As it diffuses from the solid into the air, then we're going to be changing that pressure. We do make the assumption, or at least I wrote down the assumption, that dry air means that the initial pressure of water in the air is equal to 0. Time is equal to 0. So once again, we start with just kind of our initial conditions. So if we're plotting the concentration of water, we start at something that's saturated, right? I'm going to call that C star. And we start with this all the way through the clay. But now we put it in a sealed jar of dry air where it's down to 0. So over time, we're going to start diffusing the water, all that water that's in the clay, diffusing that into the air around. But as we do that, this 0 is going to, the pressure on the outside, or the relative concentration that will be caused by the outside pressure, is no longer going to stay at 0 because now we're getting that water vapor in the air. So it's going to shift upwards and upwards and upwards until you reach some sort of equilibrium between the clay and the air in the jar. So in our short-term solution, it's moved up just a teeny tiny bit, right? Because we still have, that initial concentration within the rest of the clay. But over a long time, it's shifted up a little bit more. No longer have that initial concentration in the clay, and we're going to reach some sort of final homogenized value that again has shifted upwards. Shifts up. This, once again, is an equilibrium. Equilibrium, and that's because, again, we have that horizontal line. We've reached some sort of homogenized value where it is no longer changing. Any questions about that? Go for it. Yes. So, yes, let's imagine that we are in a room and I start to breathe really heavily. Am I going to change the overall concentration of the air in the room? What if I take a paper bag and I stick it to my mouth and I start breathing into it? Am I going to change the concentration of air in that paper bag? This is a very similar situation in that when we're in an open atmosphere, then you can do whatever you want. You can diffuse whatever you want. You're not going to be changing the overall concentration. But in something that's sealed in a small volume, we are going to be changing that concentration. Does that make sense? Beautiful. Any other questions? Soleil. So the next one is a steel pipeline transporting hydrogen. Very classic 2E question, at least when Dr. Zurab led this course. He really loves his steel. And we just need to show the final state. So I'm going to do my little box as per usual. And I'm going to say that this is inside. So this is going to have the hydrogen that's transporting. This is the steel. And this is outside. So just regular air. And so what we can think about again, we're just doing the final state here. We don't need to think about what's happening over time. So we can think that, okay, inside, we're going to have some sort of pressure of hydrogen. This is not going to be changing over time because we're going to be continually supplying more and more hydrogen because it's a pipe and it's shoving that hydrogen through. So no matter what diffuses into the steel or what diffuses out, whatever happens, we're constantly going to be supplying more and more hydrogen to replenish anything that's lost. So this is fixed. Fixed. Outside, then we're going to have some sort of concentration as well. And this is very similar to C that we talked about. So it's just air. It's a very, very big space, an open atmosphere. So any sort of changes to the hydrogen that, may diffuse through the steel aren't going to affect it very much. So this is going to be constant as well. You don't even need number here. So what's going to happen is we're going to have this continual diffusion from the high H2 inside the pipe to the low H2 outside the pipe. But these aren't going to change over time, and we're just going to continually have this concentration gradient. That means that it's steady state, because again, it's not homogenized. We don't have the same concentration everywhere, but it's not changing with time. Does that make sense? Are there any questions? Beautiful, last one of these questions. So another steel pipe, oh boy, but now we're getting fancy and we're coating it with copper. So I'm going to do the same thing. I'm going to draw it. This is going to be inside. So this is H2, this is Cu, steel, and now this is outside. H2. So once again, we're going to have basically no hydrogen outside, and we're going to have very high hydrogen inside. This is the one where I remember I started like freaking out and I was like, wait, I actually know nothing. So I had it written down on my formula sheet. What we're going to have is we're going to have some sort of, concentration gradient in copper, and we're going to have some sort of concentration gradient in steel. And the question that I always ran into was, do I connect the lines together or do I not? And in this case, we're not going to connect the lines together. And the reason we do that is because copper and steel are going to have different permeabilities of hydrogen within them, right? They can accept more or less amounts of hydrogen. So for example, copper might have all of this hydrogen that's present in it, right? It's like taking all this hydrogen from inside the pipe, but then steel doesn't want that much. So it gets kind of like backlogged at copper, and steel can only maximize, it's maximized, limited, whatever, max concentration at a lower value. So we have a little bit of a jump. What is constant between these, however, is the activity. So if you were to plot the activity as opposed to the concentration, then they would match up, but we're caring about the concentration here instead. So we have some sort of gap. And once again, this is steady state because we do have a concentration gradient that is not changing with time. And that is the last drawn question. Any questions? Beautiful, smashed through those. The next question, I remember this took me so long when I was writing this test. It was actually throwing me off. Anyways, yada, 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 introduction, and we are adding some sort of material or some sort of ingredient with a diffusion coefficient of this, and then it's recommended that you apply a thin layer. And how long do you have to wait for 90% of this product to diffuse into the skin? So a fun fact about me, I actually wrote this midterm early because I had a rowing competition, and I didn't have this sentence about you can assume any reasonable value in my test. So I was sitting there for the longest time being like, I can't solve this question. I don't know what to do. So I ended up just assuming something, and clearly that's what you were supposed to do in the first place, but it kind of freaked me out. Anyways, the point is, when you don't know what to do, just make assumptions and move on. It's better than leaving your page blank. But anyways, we're not given much information here. So I'm going to start by, the way I start all of my mass transfer problems. I find it really helpful to have kind of a basic way to approach problems, because when you get to a test, like me writing this test, and I had no idea how to do this, you're given a little bit of a head start when you already know how you wanna begin. So I'm going to start by drawing it. That is a very classic way to approach these questions, and I find it really helps me as a visual person to understand what's going on. So I'm going to say this right here is the skin, and then this is the lotion. I fully wrote it down as sunscreen in mine. I fully thought it was sunscreen when I took this test and not moisturizer, but regardless, that's unimportant. So we have our sunscreen, not sunscreen, we have our lotion and we have our skin. And we're going to start our initial condition again. We're going to have the sum concentration of our lotion in the lotion and then none in the skin. And over time, what's going to happen is this is going to diffuse into the skin. It's going to look a little bit like, oh, wait, that was our long time. We're going to do blue. Ka-chow, ka-chow, right? And then as time goes on, it's going to go down a little bit more. And this gets a little bit complicated because technically over time, this distance, as it diffuses into the skin, it's going to decrease, right? So we have to make a bunch of assumptions here to kind of simplify our situation. The first thing we can assume is that the concentration within this little block, we can say that it's just going to be horizontal. We can say that it's constant. Because it's so thin, any sort of curve that we have going on here, right, is going to be relatively minor. So when we're assuming things, we can say that it's a linear concentration profile in the layer of lotion. Assume. The second thing that we can assume is that this layer of lotion, I'll do this in black. We're going to assume that this is really, really small compared to the skin. So a couple of assumptions we can say is assume skin is semi-infinite. Skin is infinite thickness compared to sunscreen. And why this is really important is because remember that initial condition, back when we were doing our other stuff, we said that if you still have your initial conditions from your solution, then you can use that counts as a short time. So if we keep, no matter how long time goes on, if we keep this initial condition in the skin of 0 sunscreen, this means that we can now use the short-term solution to solve this question, even if we're talking about as a long time as it, almost all diffused. Another thing that I wrote down in terms of a assumption is that we can assume that the skin or the body, is thick enough to treat as a single layer. So I can also just say single layer. Because I was writing this, I'm like, do we have to account for like the skin, like it diffusing like throughout it? And I'm like, that's just ridiculous. But I was freaking out a little bit. The other thing that we're going to assume is the thickness of the layers. So again, this is a reasonable guess up to the person. I'm going to be doing what I wrote when I did this test because that'll make my numbers work better. And I'm going to assume thickness of lotion. Oh, I called it sunscreen again. Of lotion is 0.1 millimeters and that it doesn't change over time. And no change in thickness over time. Because realistically, as the lotion diffuses, it's going to go into the skin and this is going to decrease. But that just gets way too complicated. So we simplify it to make the situation a bit more feasible. And realistically, it's so small and so thin anyways, it's not going to have a significant impact. So we've done our drawings. We made some assumptions to make it a bit easier. The next thing we need to do is talk about the situation and kind of put some numbers to it. So that starts by doing our initial conditions. So the concentration, I'm just gonna add some little letters here. So I'm gonna call this direction Y, and this thickness I'm gonna call delta. So our concentration at any Y distance at time is equal to 0, because remember this is concentration at Y and T, is going to be equal to 0 for Y is bigger than delta. And all this is saying is that the concentration in this area, so where Y is greater than delta, is 0 at the start. The other thing we can say is that the concentration 0, 0 is equal to some C star. And again, this C star is what this value is. I'll write that down. And saying 0, 0 just means at the very start, at this location right here, wherever we apply the lotions. We're just saying that, hey, when you apply the lotion, there's no lotion in the rest of your skin, but there's all the lotion in the lotion area. Next, we have our boundary condition. So this is just at some sort of time. And we can say that the concentration at a large distance at any time t is equal to 0. So all this is saying is that anywhere over here, deep in the skin, that's always going to be equal to 0. We're always going to have that boundary available. So now what we have to do is figure out what equation we're going to use. And we know that it's a short-term solution. So you can go to your little equation sheet. And we have this equation right here, that C of y and t is equal to C star times delta over the square root of pi dt times the exponent of negative y squared over 4 dt. Now, actually, in my notes, I have it written down that there should be a 2 here. And you note that I excluded that right now. And the reason for that is the example we did in class in my year for solving something like this had to do with a semi-infinite block with a little wafer in between. And in this case, we were given the equation with the 2 in it. And we had that wafer diffusing into the rest of the block, and it was semi-infinite, so we could use the solution. But in this case, we're diffusing over 2 sides. With the lotion, we're only diffusing in one direction, which means that we can't use that 2 there because we're actually having it all diffused in the one direction. Does that make sense? I'm seeing some nods. Beautiful. So that's just a side note. Anyone who just looks at the notes will be confused, but that's okay. So we're going to use this equation. So now we just have to think, okay. We are, what did I do next? Yeah, so we want to solve, we can start by plugging in some of our conditions that we set, right? Our initial conditions and our boundary conditions. Do we even need to do that? Yeah, so we're trying to find the time. Yeah, I just wrote something wrong on my test, but it's fine. We're trying to find the time at which 90% of the product has diffused into the skin. So what that means, if our initial so we want to find the concentration at some time, at some distance. So we can say the concentration at y is equal to, d. So right here at the base of the skin. I lied. What we're going to try and find is we want to find the concentration at the start here. Because remember, I'm going to draw what it looks like at the time we're trying to find. If it starts out like this, remember we made the assumption that it's going to be constant here. Over small time, it's going to look something like this. But we simplify it, remember, to look like it's horizontal line. So it looks something like that. The time we're trying to find is at which this value here is at 0.1 C star, whereas this is C star. So we're trying to find is the concentration at y is equal to 0, so right at the edge, and time t is going to be equal to 0.1 C star. And that's because 90% or 0.9 C star has been diffused into the rest, into the skin, into the bulk of the body. So we're going to set that the 0.1 C star is equal to, and I'm going to leave it in parametric form right now and just say C star times delta is equal to root pi dt times the exponent negative 0 over 4 dt. Remember, our y is equal to 0 because we're looking at the surface, right, where we're applying that lotion. So what we can do here is we know the exponent of 0 is equal to 1, so we can just cancel out the entire term, and we can cancel out the C star. So you never actually need to know what the initial concentration of sunscreen was, of lotion. You can kind of just go with it as that. So now we're left with 0.1 is equal to delta over root pi dt, where delta is the initial thickness of that layer, which we assume to be 0.1 millimeters. So now all you have to do is solve for t. So we can say the root of pi dt is equal to delta divided by 0.1 t, or pi dt is equal to delta over 0.1 squared. T is equal to delta over 0.1 all squared times 1 over pi d. So now we can sub in the values. So remember our delta was equal to 0.1 millimeters. So I'm going to convert that to SI units. 0.1 times 10 to the negative 3 meters all over 0.1 square this 1 over pi, and then our diffusion coefficient, if you remember from the question, was 10 to the negative 9 meters squared per second. And if you calculate all this, I got a value of 318 seconds. So to kind of summarize what we did there, the hardest part of this was understanding how to start and understanding how to approach the question. So I always recommend starting with the drawing, your assumptions. Oh gosh, no, go back. Drawing your assumptions and then writing out your initial conditions and your boundary conditions. Using those, try and recognize the kind of situation you're using. So in this case, it was short term. We find the equation that we needed, and then you just kind of solve for it as needed and get a final answer. Any questions? Go for it. Because we put a y value of 0, because we're looking at the surface of the skin, and the exponent of 0 is 1. You're welcome. Beauty. Moving on to the next question. Making really good time here. I'm impressed. Okay, so now we have some steel, classic, and we're carburizing it, also classic. So we're carburizing it for a certain amount of time and temperature with a fixed concentration. And then we're cooling it really quickly, and we're like, oh, if we're at a concentration greater than this value, we're going to form martensite. How far are we forming that martensite on the gear? And then we're given a bunch of values. So this is a much more calculation heavy question. To me, I found this a lot more like, okay, there's a lot of numbers here. So I found all of the numbers overwhelming as opposed to all of the situation. So I started this by just writing out all of my variables, because I was like, wow, that is a lot of things. So I'm going to start. I'm just going to go through the question and kind of write things as I see them. So we start with the initial gear with some sort of carbon content. So that's our initial carbon content. So C naught is equal to 0.18 weight percent. And then the carburizing treatment is done for 2 hours at some sort of temperature. So I'm going to say T is equal to 2 hours. T is equal to 1000 degrees C. And I'm going to convert these into SI units immediately just because that's how my brain works. I don't actually know what we're going to use, but this makes me happy to put it in SI units. So we have 7,200 seconds and we have 1273 Kelvin. Next, we know that the fixed surface concentration is 0.8 weight percent. So I'm going to say the surface concentration is 0.80 weight percent. And then we know it's quickly cooled. And for any concentrations greater than 0.4 weight percent, then we're going to try and find something. So I'm going to call that C max for the maximum concentration we're looking for, 0.40 weight percent. It wants us to find the depth. So I'm just going to write D at C max is equal to question mark. So I remember what I'm trying to look for. And then it gives us a bunch of like classic thermal or heat mass transfer properties. So I'll write out, I'm just going to write them here. D naught 3.0 times 10 to the negative 7 meters squared per second. Q is equal to 100 times 10 to the 3 joules per mole. And density is equal to 7,800 kilograms per meter cubed. So I've written out all these things. I'm like, okay, at least I know what numbers I'm working with now. I'm going to start, well, next I'm going to draw it because, I have a very classic way to approach these questions. I got to draw, I got to write my variables out, and I got to write my boundary conditions and my assumptions. No matter what I do, I need to do those 4 things. So I'm going to start next by drawing it. Ciao. So we have some halfway mark. I'm going to call this right here the thickness divided by 2. And this is the thickness divided by 2, where delta is the entire thickness. And this, I'm going to write the weight percent carbon on the edges. Initially, we're going to have fixed on the edge 0.8 and 0.8 down to 0.18, because remember, that was the initial condition. 0.18. I'm also going to call this CS and C naught. And then over time, we're going to have it diffuse in to form our martensite, or to form the potential for martensite, increase the concentration. But note that we're still going to have that initial concentration in the middle. And we're going to assume that it's never going to reach the long-term solution here because we're only heat treating it for 2 hours. So that's one of the assumptions we're going start by making is assume 1. Sample is large. Therefore, short-term solution. If you had a really, really thin wafer of steel and you put it in these conditions for 2 hours, it's likely that you would diffuse so much, you would get something like that. That's a long-term solution. But we can assume that our sample is large enough, we're not going to reach that state. The next thing that we can assume is that the diffusion distance is pretty small. Small diffusion distance. So we can approximate linear geometry. I think this is one of the assumptions for using the error function. I honestly don't remember, but I'd written it down on my formula sheet as one of the assumptions to make. So that's something to kind of keep in mind. Another assumption that you can make, again, these are just assumptions that had been brought up in tutorial and I'd written down on my formula sheet or my cheat sheet to make sure that I remembered to say so I didn't lose any marks. So another assumption that we can make is that it's immediate diffusion. Diffusion. So no incubation time. Sometimes for certain reactions, let's say you put this hunk of steel inside the carburizing furnace, it'll take a little bit to like maybe heat up to the temperature of the furnace, right? To undergo that diffusion property. And that means that you wouldn't actually get the same amount of diffusion as you might calculate here because you have that time at the beginning where it's not actually diffusing. And we're just going to assume that doesn't happen. So we've loaded some assumptions, we've done our drawing, we have our givens. The last thing to do is to write down our initial conditions and our boundary conditions. So we kind of already wrote this in when we were talking about like C0 and CS, but regardless, we're going to make it really obvious so we get all of the marks on our test. Our initial conditions, so we know that the concentration at any distance, so along the entire line, at time is equal to 0. That's equal to our initial concentration, C0, which is 0.18 weight%. Our boundary conditions, the concentration at the surface at any time t. Remember, this is fixed. Oh no, that's the wrong pen. This is fixed here, right? We're in some sort of carburizing furnace where we're fixing the surface concentration. It says that in the question. So no matter what time at a distance of 0, then we're going to have, call this y. Then we're going to have the same concentration, CS, at the surface, which is 0.8 weight%. And then the concentration at distance delta over 2 and any time t is equal to C0, which is equal to 0.18 weight%. And what we're saying here is, again, that we're using a short-term solution. So we're saying that no matter, how long you keep it in the sample, within reason, we're never going to reach that long-term solution. We're going to keep some sort of that initial concentration in the middle so that we can use this short-term solution. Back up. This is where I goofed, and I actually forgot how to use error functions. Fun fact. So, where'd my sticky note go? I had a sticky note, and it just since disappeared. Oh, I found it. There's a few different ways that you can approach this. But we know because it's a short-term solution, that we are going to be using the error function here because we have one substance diffusing into a mixture. So what I have in general, I need to get more space here. Oh no, that's not what I meant to hit. In general, when we're talking about our short-term solutions, we have the concentration at y and t is equal to a plus b times the error function y over 2 root dt. That's the really general equation. And there's a lot of different situations that you can use and you can try and like memorize them, put them on your formula sheet, whatever. Worst comes to worst, you can take these initial conditions and these boundary conditions, sub them into there to get the appropriate function. We can just take a shortcut and write that the C at y of t is equal to the CS, which is the surface concentration, plus the difference between them, so inside minus CS, times the error function y over 2 root dt. So we're going to start by using this equation. And we look at this and we're like, okay, let's see what we know. We're trying to find, well, we know CS. We know CI minus CS, where CI is C0. I'll rewrite it using C0 minus C0. we're going to be looking for some sort of y, because we know the time we're looking at, right? So we're going to be looking for some sort of y. We know the time that we're looking at. What is d? What is that diffusion coefficient? So some might think, oh, Sarah, it's right there, d naught. But remember, we're looking for a diffusion coefficient, not d naught. I forget exactly what d naught is, but it's only part of it. So before we can plug anything into this equation here, we need to start by finding our diffusion coefficient. So we can use the equation d is equal to d naught exponent of negative q over rt. And from here, it's just a matter of plugging and chugging. So from the question, we know that d naught is 3.0 times 10 to the negative 7 meters squared per second times the exponent of negative 100 times 10 to the 3 joules per mole, that's our Q value, over 8.314 joules per mole Kelvin for R, and 1273 K. You'll notice that I always include my units when I'm writing out these equations. I find it's a really handy check when I'm writing out questions to make sure I don't miss anything, or like forget. Sometimes I just forget to put in certain variables to my equations. So this way it's just a really quick check to be like, okay, all the units cancel out. I know that I should be at least decently close. But anyways, if you calculate this, you will get a value of 2.364 times 10 to the negative 11 meters squared per second. So from this, we can go back to our initial equation, and we can start looking at that and plugging it in. So we know CS. Again, we know CS, C naught CS. Now we know D. What we just need to think about right now is the concentration and the time. So we'll go back up to our question. It's asking us to find the depth that we can find hard martensite. So what we're looking for here is we're looking for the X value, or I guess the Y value. We're looking for the Y value at which we find that martensite at some sort of 0.4, right? So we're going to set the concentration of 0.4 and solve for Y at a time of 2 hours. So the depth, or the concentration we're looking for, is 0.4, and that's going to be equal to the surface concentration, which was 0.8 plus 0.8 minus 0.18 times the error function of Y, because again, we don't know that depth, over 2 the square root of 2.364 times 10 to the negative 11 meters squared per second times that 7,200 seconds. Again, we need to make sure we're in SI units here, just so that if we put in hours there, we're going to get a totally wrong answer. So if you calculate this, we would end up with, I actually did this slightly differently on my test, but I don't like the way I did it. So you're going to end up with 0.4 is equal to 0.8 plus 0.62 times the error function of Y over, oh, we'll put in the positives, 1211.937Y. I think I was just a little extra when I did this on the values. So now we're just going to rearrange and put 0.4 minus 0.8 divided by it. Oh, because I swapped these around. Okay. So it's Z naught minus CS, so 0.18 minus 0.8. Beauty used to be minus 0.62 is equal to Earth of whatever it was. So now we're going to end up with the value of 0.6452 is equal to the error function of 1211.937y. But we can't just plug into our calculators, hey, give me the inverse of the error function, right? We need to look up the error functions in the textbook, or I think they were on the back of this test. Yeah. So Dr. Zerb was totally fine with you reading it off the graph. Personally, I'm not a big fan of graphs. I like my numbers. I'm a numbers kind of girly. So I prefer the method of linear interpolation. And whenever I think of linear interpolation, then high key, I always need to write out the equation so that I don't forget how to do it. So let's say that we have some value A, B, and then we have X, and then we have their associated values, F at A, F at B, F at X. And X is unknown, but A and B are both known. The way that we can linear interpolate, or the way that I like to linear interpolate, the way that I do it, is I do B minus X over B minus A is equal to f of b minus f of x all over f of b minus f of a. And whatever is unknown, you can find it. So in this case, we know that we're going to call this value within the error function x. And this value here is f at x, because that's what the error function is equal to. And then we can look at the error function in the textbooks to find the matching values that would surround this f at x. So what you'd end up getting is you would have, oh, I did it differently when I did it back then. No, I can figure it out. So we are going to have 0.70 minus x is over 0.70 minus 0.6. One sec. What did I do here? I'm not sure I did this right. Sarah, you silly girly. We'll do that right now. Okay. So we can go down to the table. And we're looking for where f at x. Oh no, I definitely did this right. Yeah, I lied. We are looking to find x. So we want to have some values that surround f at x because that's our value. So we're going to have our f of x value, remember, is 0.6452. This is f at x. So we want to subtract it by something that's slightly bigger than it. So 0.778, because if you look down at the table, ka-chow, we have, oh, don't die on me, one note, don't die. Okay. Our ERF was, like the f of x or the ERF of z, was equal to 0.6452, which is right. It's going to be right in between these two values here. So we're going to take the 0.65 and the 0.7 and try and find something in between here. So we're going to be linear interpolating between those two. So those are where I'm getting the numbers from. I keep tripping myself up there. So then we'll end up with 0.6778 minus 0.6420. No, over 0.65. And anyways, you can solve this either by rearranging or by just honestly plugging the entire thing into your calculator and saying solve for x. Whatever floats your boat, you will end up with saying that x is equal to 0.6545. And you might say, great, that's the depth we're looking at. But remember, this is solving for the inside of whatever ERF function is, right? But we remember that we had ERF of 1211.937y was equal to that number, which is equal to the error function of what we called x. So in this case, 1211.937y is equal to x, which is equal to 0.6545. So you can solve for y, which is the depth, 0.6545, divided by 1211.937. And you'll end up with a value of 5.4 times 10 to the negative 4 meters. And that would be your final answer. Any questions? Beautiful. We have one more question on the test. This one only took me one page, so I think it's my favorite. The other ones I had to write on the backs of pages, so. Okie dokie. In order to measure the diffusion coefficient of argon in PET, then we're using a spherical chamber with some values, and we're initially pressurizing it, and we want to check the change of pressure in the chamber walls. Then we give it a bunch of values, and we want to estimate the diffusion coefficient. So again, this is a lot of numbers, so I start by just writing everything down. So we have a diameter of 10 centimeters. D is equal to 0.1 meters. I'm just going to write immediately that the radius then is going to be equal to 0.05 meters. And we're given some sort of thickness. I'm going to call that delta of 0.5 millimeters. 0.5 times 10 to the negative 3 meters. And we're initially pressurized to a pressure of 5 atmosphere. So I'm going to say P initial, PI is equal to 5 atm. And then we track the change in pressure through the walls. And we know that dP over dt T is equal to negative 5.6 times 10 to the negative 7 P inside, where P inside must be in pascals. This is important because the pressure we were initially given was in atmospheres. So now we are assuming that we follow the law CAR is equal to 1.91 times 10 to the negative 5 PAR. Again, this is in pascals. We want to estimate the diffusion coefficient. So we have to start this one. I didn't actually make a drawing because I recognized from the get-go what kind of situation this was. But we can start by making a drawing just in case to help recognize in case you have to do something like that on the test. So we have some sort of chamber. I'm just going to draw the layer of PET. So this is PET, this is outside, and this is inside. So inside, we're going to have some amount of argon initially, right? The initial, and outside, we're just like, there's no argon in the gas, unless I'm a fool, but we're going to assume that this is equal to 0. So initially, we have this nice little, square concentration gradient. And what's going to happen over time, this pressure, inside or outside, this isn't going to be changing because, again, we're in that open atmosphere. You can put within reason, you can put more gas into the air. You're not going to noticeably change the pressure or the partial pressure of the gas. It's just going to immediately diffuse away, and it's going to be minor compared to the gases that are already present. So we're going to assume that this pressure is constant, or it's fixed, is equal to 0. So over time, what's going to happen is we're going to take the argon that's inside, it's going to diffuse through the PET, and then go outside. And what's going to happen is as you do that, the pressure of the argon inside is going to decrease and decrease. But keep in mind that outside, it's not changing at all. So our concentration gradient is going to look something like this, where it just keeps going down and down. So along with this, we made some assumptions, right? So we assume the argon outside is equal to 0. We can also assume room temperature, T is equal to 298 K. We can assume that argon behaves as an ideal gas. And we can assume the volume is constant, so that the PET isn't shrinking as it loses this argon. And now I have to recognize what kind of situation this is. So what we have changing here is that we have this pressure is changing. We have one concentration changing. However, the thickness of this and the outside pressure are not changing. And because we only have one of these variables changing, we can assume pseudo steady state. So I'm going to write that as well. Assume pseudo steady state. So we know that we're going to be assuming steady state, and some of these assumptions you might not have recognized you needed to make immediately. So we can come back to them and see, okay, why do we need to make that assumption? But the big thing to recognize from this, are you raising your hand for a question? Okay, beautiful. So valid. The big thing to recognize with this question is really understanding that we are dealing with pseudo steady state here. The big way that we did that is by recognizing that a lot of the variables here are not changing. It's just the one concentration that is. So we're going to start by writing out Fick's first equation, I believe it was. Maybe I'm totally lying, but J is equal to negative D C. Oh gosh. My laptop's also dead in the middle. So whenever I try and write there, it's kind of sucks. C2 minus C1 all over delta. And this is again coming from, the long form equation. J is equal to negative D di C over di Y. whereas the change in concentration is C2 minus C1, and the change in Y is just going to be the thickness, which we're calling delta. This is just a little bit easier to handle. So we can just from the get-go, we know that the concentration outside is 0. C2 is 0 because it's outside. We also know, so actually we're going to do this multiple steps. So we know that it's 0 outside. So now we're left with J is equal to, we can cancel out the negatives, d C1 all over delta. But we're not given concentrations here, right? We're given our pressures. But luckily we have this equation. We were given a way to convert them to each other. So I'm just going to sub that right in for the concentration inside. So now we're given it's equal to d, I'm going to call this right here K star, just to make my life easier. D K star P inside, initial, all over delta. So we can look at this and we're like, okay, we're trying to find D. We know K star. We know the initial concentration or the initial pressure. We know the thickness, but we don't know everything, right? We don't know how this pressure changes over time. So we can't solve this yet. We can't figure out what the diffusion is yet. So this is where we need a second equation. And the way that we do this is by looking at the alternative equation for flux, J. So another way we can write J is J is equal to 1 over A dN dt. And you're like, Sarah, that literally doesn't help us at all. We don't know any of these values. What are you talking about? But remember these assumptions we made. We assumed that we are an ideal gas. So ideal gases, we can use the equation PV is equal to nRT. So N, therefore, is equal to PV over RT. If we're doing dN over dt, that's going to be equal to the derivative with respect to time, PV over RT. And now we go back to our other assumption where we said that assume that the volume is constant. That means it's not changing with time. So our volume isn't changing with time. R is a constant. That's not changing with time. Our temperature, again, we also assumed that previously. So it's another way we can figure out we needed to assume our temperature. That's not changing with time. So we can pull those out of the derivative here and say V over RT times dP over dt. dN over dt. So now we figured out a much more useful relation than dN over dt. We can sub that back into our flux equation. So now we would end up with J is equal to 1 over A times V over RT dP over dt. So now we have a better relation for what our pressure is, because remember in our initial flux equation, we had no idea what that is. We just know the initial situation. And we have two equations for J that now make a little bit more sense for a situation. We can set them equal to each other. So now we can say D over K star dI over delta is equal to 1 over A V over RT dP over dt. And now we're going to rearrange and solve. Oh, computer, please cooperate. We're going to rearrange and solve because we have a lot of variables here. And we have to remember that we're trying to solve for the diffusion coefficient D. So I'm just going to throw everything else on the other side. I'm going to say D is equal to, I'm going to move it over here. D is equal to delta over K star P times 1 over A V over RT dP over dt. This is a lot of variables, but we're going to add actually more variables. Hooray. So what we're going to do is we're going to, remember this is a spherical chamber. It says so in the question. So spherical, we know that A is equal to 4 pi r squared, 4 pi r squared. V is equal to 4 over 3 pi r cubed. And then we also remember, we can also sub in our value for dP over dt. Remember, we were given this in the question that was equal to, I'm going to call this, instead of number times P, I'm going to call this right here, I'm going to call this We'll call it C. Is it? Why did I say C in the? I don't know why I called that C. We're gonna call this F times P because F is a good letter. It doesn't get used enough. F times P. Oh gosh, computer, can you behave, please and thank you. So now I'm just going to take all these and sub them in to hopefully make this a little bit better for ourselves. Delta over K star times P over 1 over 4 pi r squared 4 over 3 pi r cubed over RT times FP. And now we can cancel out many, many things. So the first thing, r squared and r cubed cancel out. The 4 pi's cancel out. And then we also note that our pressures cancel out. Look at that. So now we're left with our diffusion coefficient is equal to delta times r times our whatever we named f all over K star times 3 times RT. And this is much more manageable. So what we can do now is plug in our values. So this, our thickness, remember, was 0.5 millimeters, so times 10 to the negative 3 meters. Our radius was 5 centimeters, so 0.05 meters. Our F value was that number at the front of the dp dt, which was 5.6 times 10 to the negative 7. All divided by 3. And then our K star was in the equation for figuring out what the concentration was. So that was 1.91 times 10 to the negative 5. K star. R 8.314 joules per mole Kelvin. And then we're left with T, which was 298 Kelvin. If you plug all this into your equation, to your calculator, I know words, you will end up with a value of 9.86 times 10 to the negative 11 meters squared per second. And there's a couple of checks you can do for this. The first is just kind of a bit of a intuition check. Is this a number that seems feasible? So if you look back at our previous questions, or if you think back to any practice questions you've done, this is about the order of magnitude you'd be expecting for a diffusion coefficient. Another thing you can do is try and do, again, a unit analysis, because we know the units for a diffusion coefficient should be meters squared per second. That gets a little tricky in this question because when you look at either F or C, the values there get a little iffy. But if you're like really extra, or in my case, really stressed about screwing up your derivation, that is also a valid way to check your answer. But that is the end of that question, and that is the end of the midterm. So for reference, that took us about an hour to go through. And we were given, I believe, 90 minutes for the test. Yeah, we were given 90 minutes. So, hooray, any questions? I'm gonna check in online because I have not heard an inkling from any of them. I'm sure they were just like obsessed with staring up my nose the entire time. That's my favorite thing about online review sessions and sharing my screen, is because I know I just look incredible. But I think that keeping my camera on helps because I use my hands a lot. Okay, I'm not seeing a single question. So with that, I'm going to stop recording. So again, if folks have questions, feel free to message me or shoot me an email. I'm happy to chat. Thanks for stopping by, and best of luck with the midterm. Slay. Wait, I totally forget how to stop recording, guys. I'm actually like, I haven't, okay, I figured it out. I haven't used MS Teams in so long.